So we're just a little after 1. Let's go ahead and get started. So my name is Taylor Brown. I'm a senior program manager on the HyperV team. Some of you might know me. I used to work on the HyperV test team. Now I'm a program manager on the team. And my primary areas of focus are migration scenarios and our user mode stack. I'm actually filling in for one of our other program managers who owns storage right now. So in Windows Server 2012, we introduced support for virtual machines running on SMB shares. We're storing virtual machines on SMB shares. So this includes both our virtual hard disks as well as our configuration files, any snapshot information, or any other relevant Hyper-V virtual machine settings. So really the goal of this is to enable a bunch of new scenarios, including just being able to run on a SMB share. But in addition to that, it enables things like our shared nothing live migration, in which case we can move a virtual machine's hard drives as well as its memory state to another server without any downtime. We also can enable cross-cluster live migration, which allows us to move a virtual machine running on one Hyper-V cluster to another Hyper-V cluster without any downtime. These all build on top of our SMB3 support. Now this works for both standalone and clustered Hyper-V servers, as well as standalone and clustered file servers. And it is required to have SMB3 support for this functionality. And these are kind of the reasons. These are the main functions that we're using for SMB3. So we use transparent failover. This enables some key scenarios that we'll go into. We're using scale-out file servers for SMB scale-out. SMB direct for performance, multi-channel. We can enable encryption of SMB for security, VSS for backups, and PowerShell and VMM support for configuration and management. So one of the big considerations for Hyper-V is always availability and resiliency. We need to make sure that virtual machines continue to run under as many conditions as possible. Now obviously there's going to be some conditions, such as a host going down, where we can't keep the virtual machine running. We have to restart it. And in those conditions, we want to make sure that we've got resiliency, that we can recover from that failure as quickly as possible. So with that, a couple of the functionalities that we did for handling intermittent network failures. So we've got a virtual machine that's running on a file server, normal operation, everything's great. We have a temporary disconnection. Someone unplugs the network cable, we have a switch failure, something like that. The connections can be reestablished without any application downtime, assuming that the connection lasts, or the disconnection lasts shorter than 60 seconds. And we accomplish that by using SMB persistent or durable handles. So the virtual machine, the Hyper-V server, opens a file handle to the file server with a GUID, an application identifier. And if the connection is disconnected, the file server remembers the handle state, remembers exactly where everything was running, and allows the virtual machine to reconnect automatically without any downtime within that 60-second period. So in this case, we can handle a complete network failure with a single path. The second one is handling either permanent network failures or network failures when we have multiple channels. So in this case, we've got SMB multi-channel, so we have 2 connections to the file server, both running. We have a disconnection, or permanent disconnection of one of the network adapters. The connections are handed over and failover occurs, and the virtual machine is none the wiser. All the applications continue to run, although at a slightly degraded state, right? We can't take advantage of both the network connections anymore. So if there was a high-performant workload, you'd have a little less performance, but the application continues to run as expected. And if this connection came back up, then the virtual machine would continue to use both connections just as it did before, without any downtime or problems for the application or the virtual machine. So continuous availability. This is for a file server node. So we've got a continuously available file server with a share, the virtual hard disk on it, the virtual machine is connected to that one. If we have a failure of that file server node, the share automatically moves over to the other file server node completely transparently. The connections are reestablished, the virtual machine continues to run without any downtime. So the virtual machine doesn't restart, the applications aren't aware of it. There's a temporary I/O blip while the handover occurs, but everything is persisted. And the way we do this is that all of the handle information for the virtual machine or for any connections is actually stored on the storage that we move across. So when we move it across, the other node reads that information in, It understands about all the handles. It understands about all of the connection state. And those connections can be reestablished automatically. Now, what about a Hyper-V node failure? So remember a minute ago I talked about we send this identifier down so that if there's a temporary network disconnect, we can reestablish that connection. Well, that's kind of what a Hyper-V node failure looks like. So we've got a virtual machine running on this Hyper-V cluster. That node goes down. That looks like, from the file server standpoint, a temporary network disconnect, right? It doesn't know that the actual node crashed. It just knows there was a handle open that just went away. So what we do in this case is we use something called cluster client failover, CCF. So when it moves over to the other side, it sends down a key, which is the virtual machine's ID, to the file server, saying, hey, I need to go access this file. The file server understands that this connection just came from a different source application, different node, and allows that file handle to open immediately without any downtime. Otherwise, we'd have to wait 60 seconds for that to time out and in order for the connection to be reestablished. So these are the three main examples of areas that we wanted to make sure we invested in to ensure that virtual machines could continue to run reliably and highly availably in Hyper-V scenarios over SMB. The next big area was scalability and efficiency. So with SMB, we've got something called scale-outs now. So what we've got here is we've got a number of cluster shared volumes, shared storage of some sort, and we've got a single file server namespace comprised of multiple nodes. Now, these nodes can be added to or removed to at any point in time. So we could take this from 4 all the way up to 8, or we could take it from 8 down to 4 all the way down to 2. And the throughput scales linearly as we do that. So as we add more nodes, we get more throughput. As we reduce the number of nodes, we get less throughput. Similarly, we support up to 64 nodes in a Hyper-V cluster. So effectively, as you grow your infrastructure, as you add more Hyper-V nodes, you can, in response, add more file server nodes to handle that application load. And this is all done without any downtime, without any unavailability. And it's all fault tolerant. So if half these nodes went down, the other half will just pick up the workload. Right? So this is a key element to our ability to scale out both I/O workloads as well as compute workloads for virtualization. Now, in Server 2012 R2, this is a new feature that was just introduced. We automatically rebalance scale-out file servers. So in this example, we've got a Hyper-V server that's talking to this node. This file share will automatically be redirected, and the node will be redirected to access this other node automatically so that we can balance the load across the different file servers. Now, the reason we want to do that is that each node effectively owns one cluster shared volume, or many cluster shared volumes, but generally it's going to be one or two. And we want to make sure that that load is balanced out across the nodes so that we've got, we avoid any sort of redirection traffic or any sort of overhead, and so that we balance the load into the file servers. And this is done completely automatically now. So as if we had 5 cluster shared volumes, one of these nodes would own 3, one of them would own 2. If we added another node, 1 or 2 of those cluster shared volumes would automatically move to that other node. The connections would be rebalanced automatically with 0 downtime over about a 5-minute period, and the applications would continue to run now with more throughput available to them. Right? Another key feature that we've done is the ability to do an unmap command. So space that's in a thin pool or space that's thin provision can be unmapped from the virtual machine all the way through the SMB stack, all the way through the file server stack down to the underlying storage. So for example, you had a thin pool with, let's say, 10 VMs running on it, and someone copied a file into one of those VMs. Let's say it was a big Access database, a couple hundred meg, maybe a couple gigs. That gets deleted later on. The virtual machine understands that that space is now deleted. It sends that allocation information down to the Hyper-V server. The Hyper-V server can then send that all the way down through the SMB stack, all the way to the underlying storage, which could be either a Windows file server backed by third-party storage, or it could be a third-party SMB server as long as it understands unmap. And now you can take advantage of that being free space. Now, additionally, we will also kind of keep this thin space we'll keep the concept of this thin space in our stack. So even if you don't get rid of it, we will reuse that space first before we allocate new. So we keep a list of kind of the space that's been previously allocated that's unallocated now. We'll reuse that first before we go ask for new. Yeah, question? Is the trim or unmap command coming from the client? Yes, it is. So the Windows server will send a trim or unmap, and that now transcends all the way through the virtual disk stack, all the way down through the Hyper-V layer, down through the underlying storage protocols. So yes, your client does have to understand an issue trim and unmap, which is done for Windows 8, and Windows 8.1, Windows Server 2012, Windows Server 2012 R2, and some third-party OSs as well. And this is supported for VHDX files and pass-through disks, which is generally unused in SMB scenarios, but on virtual SCSI or virtual fiber channel. So. The next big one that we did is offloaded data transfer, or ODX. So what ODX does is it allows either the guest or the Hyper-V server to issue an offloaded data transfer. So a good example of this would be creating a VHD. So we're going to go create a big fixed VHD. That's going to be, let's say it's 100 gig of zeroed space. Well, normally what we would do in the past is we would say, okay, we'd like to create a new file, give me some range, zero it, read the next range, zero it, read the next range, zero. And this would take a significant amount of time. What we can do now is we can just send down to the array, hey, please give me a block range equal to 100 gig of zeroed space. And the array can go do that on its own, either by having its own space set aside or doing it in the background. Similarly, if we did a file copy, so let's say we actually had two virtual machines that were both backed by the same storage, and a client, another user over the network, copied a file from this one to this one. That will transcend the entire stack down and all the way to the underlying storage and say, hey, go copy this file for me. Right? So it's completely agnostic from the client standpoint, but we will take advantage of the underlying facilities of the storage to do that operation. Now, additionally, this is kind of neat because in some way we just told you about duplicate data. Right? And in some way we just said, hey, go take this block range and make a copy of it right over here. So there's some great opportunities for things like deduplication or caching to occur because there's knowledge of this duplicate data. So performance. This is really where we made, oh yeah, question. Both, yeah. So we introduced this in 2012. ODX was introduced in 2012. And obviously it's still supported in 2012 R2. Another question? So performance. This is where we made a number of our major investments, and the first of which is SMB multi-channel. So what SMB multi-channel allows us to do is to utilize multiple network adapters, either on the client, the server, or both, to aggregate throughput. So in this example, we've got a single 10 gigabit RSS-capable NIC. So the SMB client, this would be the Hyper-V server, can create 4 different channels in order to utilize 4 different physical CPU sockets through the 10 gigabit switch all the way down to the SMB server, which effectively will increase the throughput considerably. So without the ability to do that, we might be only able to get 4 gig or maybe 6 gig of throughput through a single 10 gig NIC. With RSS and multi-channel, we can easily saturate that 10 gig network adapter. And this whole communication is done as a cooperative handshake between the client and the server. So if, for example, the server could only support 2 RSS queues, then the client would only issue 2 connections open to that server, or vice versa. The same thing happens if we have multiple 1 gig network adapters. So in this case, the Hyper-V server has 2 1 gig network adapters, and the SMB server has 2 1 gig network adapters. We'll create 2 connections to the SMB server, effectively doubling our throughput, as opposed to previous SMB 2.0 support where we only had the ability to do 1 at a time. We can do the same thing with LBFO. So we've got a NIC team. We can create 2 connections through the individual NICs, so effectively 4 at the top end, all the way down to the server. And if we have multiple RDMA NICs, we will take advantage of RDMA and create multiple RDMA connections, as well as we'll create a failover connection on any additional network adapters that are there. So if you had a server that, say, had 2 RDMA 10 gig network adapters and 2 1 gig network adapters, we will use the RDMA adapters first because they're the best choice, they're the fastest. If that switch went down for some reason, we will fall back to the 1 gig adapters transparently, obviously with less throughput, but without any downtime or application unavailability. So this is really a key area of investment that we've made in the SMB protocol. The next big area is SMB direct. This is SMB over RDMA. So we've got RDMA adapters that are exposed through the kernel, so we can do transfers without ever having to transcend into user mode or into the actual TCP stack. We can just do it directly through kernel mode offloads. This really improves our throughput as well as our latency. So we get a much faster connection with lower latency all the way through the stack. And this is fully supported with SMB multi-channel. So if you have multiple RDMA adapters, we will use multiple RDMA adapters. You can have 10 gig RDMA adapters, you can have 40 gig RDMA adapters. You can have 56 gig RDMA adapters, it's up to you. We'll utilize them irrespectively. Now the one comment about RDMA is that you have to have the same underlying protocol. So for example, we support iWarp, ROC, or InfiniBand. You have to have the same both sides. So it has to be, if it's going to be iWarp, it has to be iWarp on both sides. If it's going to be InfiniBand, you need to have InfiniBand both sides. And this is because the actual RDMA protocol is vendor specific. So for example, Mellanox and Intel don't work together through RDMA. The other key thing about RDMA is if you're going to use RDMA, you don't want to use network teaming on top of it or have a virtual switch on top of it because that effectively removes the ability for us to do that RDMA adapter transit. So in 2012, we did a bunch of work to make SMB over RDMA even faster, specifically for small workloads. So we've got a 50% improvement in small I/O workloads with SMB Direct. This increased from about 300,000 IOPS to 450,000 IOPS per interface. So if you have 2 interfaces, you're going to see that doubled for small I/O workloads. We really did this because we started to see that things like OLAP databases and SQL databases and whatnot that were issuing these smaller IOs, 8K IOs, needed the additional throughput. And it really tried to optimize our 40 gig and 56 gig scenarios. This is the direction we see people going in. We see people starting to spin up servers with multiple 40 gig adapters or multiple 56 gig adapters for their storage in order to take advantage of these technologies. And you'll expect that we'll continue to invest in these areas as we go forward as well, making sure that our SMB story is as fast as possible, both client and server. We also did something else that's pretty neat. We introduced live migration over SMB for HyperV. So now we can do a live migration of a virtual machine either over TCP, which is what we did previously, compress over TCP, or through SMB, which buys us the ability to use both multi-channel and SMB direct. And this is actually a real workload that I measured yesterday. So with TCP, it took 165 seconds to live migrate a number of VMs. I think it was 30 VMs. With compression, it was down to 115 seconds, which is great. With SMB Direct, it's 20 seconds. This is over the same network infrastructure, 2 10 gigabit RDMA adapters. Right? So you can see the massive amount of savings that we get by using SMB Direct for this operation. And while this doesn't look like a whole lot when you look at one server, when you start stacking it up and saying, okay, I'm going to live migrate the same 30 or 40 or 50 virtual machines from one node of a cluster to the next node of the cluster, the next node of the cluster for patching or maintenance operations, that time delta becomes very significant. It means that a patching operation goes from multiple days down to 1 day. Right? And if you're doing this during an outage window, that means you're not working over a weekend. It means you're able to do it in an afternoon or an evening without having to have a huge maintenance window. So this is really a pretty significant investment that we've made. One of the considerations, though, is how do we do the bandwidth management when we're now doing live migration and storage over the same network? And really, there's 3 scenarios that we're concerned about. We've got the ability to download VHDs. So we were going to do something out of a library, copying it from one file server to another file server for provisioning, those kind of things. We've got the actual SMB access from the virtual machine, and we've got the live migration. And what we don't want to do is we don't want to have provisioning or live migration take away from the SMB storage that the virtual machine needs to do its application workload. So what we did is we introduced bandwidth management. So now we can specify 3 different categories: default, virtual machine, and live migration for the different access types, and give those a limit in terms of megabytes. So default, we've got a 100 megabit limit. Live migration, we're limiting that to 500 megabit. Storage, no limit, right? So when we start a live migration, we're going to cap it up to this amount, ensuring that the storage has access to, or the virtual machines have access to that storage automatically. And this works with SMB over RDMA. This works with SMB multi-channel. This works with SMB without multi-channel, as long as it's SMB3. A couple other big advancements that we did in the HyperV layer. We're now able to online shrink or expand virtual hard disks, VHDX files. So this works whether it's on SMB storage, works whether it's on cluster shared volumes or local storage, doesn't really matter. But now we can expand or shrink a VHDX file while the virtual machine's running without any downtime. So this was really a feature that we've been needing to do for some time, and we got it into 2012 R2 through a lot of happy fanfare. And really this comes down to the ability to keep workloads running all the time. The next big one was we introduced storage quality of service. So now on a per virtual hard disk level, for each virtual machine, we can specify a minimum and a maximum amount of IOPS that virtual machine can do. Now these values work on the individual server. Maximum obviously will work anywhere. You can cap the virtual machine and say, this virtual hard disk is only allowed to do 100 IOPS, or 1,000 IOPS, or 10,000 IOPS, whatever you want to do. And we will ensure that virtual machine on that virtual hard disk does not get more than that amount of IOPS. Now, being as per virtual hard disk, that means you could say, for this given virtual machine, the VHD that's going to have the transactions on it for SQL, that's going to be allowed 10,000. But the database VHDX, that's only going to be allowed 3,000. And we will cap those independently of each other. Now, the minimums provide alerts when the virtual machine is not meeting its requirements. So if you've got, let's say, a virtual machine on host 1 or a virtual machine on host 2, they're running to the same SMB server. That virtual machine on host 1 is not meeting its minimums. There will be an alert fired so that you can take action against the either the storage or the virtual machine in order to ensure that it can meet its minimum SLAs. We also added some attributes to our VM metrics, including average normalized IOPS and average latency. So now we can give you those measurements as well for any virtual machine or collection of virtual machines on a HyperV server. So backup and restore, this was one of the other key areas that we wanted to ensure we did for SMB. So in this example, we've got our HyperV host, which has got a virtual machine on it. It's got a remote VSS provider, the VSS service locally on it, and some backup agent that's going to request a backup. Now that virtual machine is running on remote storage. So how do we get a consistent application backup? The backup agent calls the VSS service, says, I'd like to back up this virtual machine. That calls down through the remote VSS provider to the remote VSS agent on the file server and all the way down to the VSS service on the file server itself. It creates a snap of the underlying storage and presents that in such a way that the Hyper-V server can get access to it. And the backup agent then accesses that snap to go get the volume and application-specific data off out of the backup set. Right? So we enabled full end-to-end backup support for virtual machines running on a Hyper-V server all the way down through the file system stack, through the SMB server, and back up to the backup application. The real key here is we wanted to ensure that we had no change in flow for people who went from file-based storage, block storage, to protocol storage. So with that, I want to make sure I've got plenty of time for questions. No questions. Yeah? Yeah, question over here.
We're going to want to learn a little bit more about what the protocol looks like when Hyper-V is running on top of SMB. We're using SMB as a transport
So it's just it's a typical SMB connection. So we open the file, we open a VHD file with unbuffered write through I/O, and access it. So there's really not a huge difference.
The real difference is at the requirements level, right?
Yep.
From the CA perspective and,
Yeah.
and other items that you just discussed.
Yep. So you need to make sure you implement the SMB3 protocol, and really for the main Hyper-V scenarios, the big things are CCF, cluster client failover. That's probably the area that we've seen so far the most problems in terms of third-party testing. And for availability, we really want to have scale out or CA availability. And ideally, we want to have multi-channel support. Those are really the key components for Hyper-V.
We've heard partners report issues on some of the locking areas, that Hyper-V is very intensive with some of the locks. Have you heard that?
I haven't heard anything specific, but the key thing is that we will lock. So anytime a virtual machine is running, or anytime that there's a virtual machine, we will lock the configuration files, and we will lock the virtual hard disk when the virtual machine is running. Now, in the case of a live migration, we are very specific about how we lock and unlock the files in such a way that we ensure that no one else kind of sneaks in and grabs a lock and causes an outage or an unavailability. So we use some of the artifacts of CCF for that. So during a live migration, we'll live migrate the VM over. And what we'll actually do is we'll create a handle. We'll do an open on the second node, and then wait for the first node to close the handle, which immediately grants access to our handle that's pending on the second node. So those kind of patterns are pretty important. And those are all standard aspects of the SMB3 protocol, but they're heavily used in Hyper-V scenarios. Just over here.
I have two questions. One is, can migration happen over WAN?
Can migration happen over WAN? So we actually don't have a requirement for live migration in terms of bandwidth, a hard requirement. If the connection is slow or has high latency, what we'll usually see is we'll see a long blackout period, which we would kind of define as no longer being a live migration. At the point in time when we lose a TCP connection, then it's no longer effectively a live migration. So it depends a little bit on the workload. Our general guidance has been at least 500 megabit of throughput. That's kind of the minimum bar for most applications. Now, I've had migrations that worked under 100 megabit. It just depends on the workload. But those were really kind of catered to be light workloads specifically to try to meet that objective.
And the second one is the bandwidth limits. How did you guys choose these numbers? Like 100 MB, 500 MB?
So those are configurable, I believe. I'll have to double check, but I'm pretty sure those are configurable values. That was the original specification. Yeah. So those are configurable values. So you can choose whatever values you want. Those are the samples and the defaults that we came up with. And really, that looks at a 10 gigabit NIC. A single 10 gig NIC is kind of the echelon. And our experience has been that most of the time when people are using SMB storage for all their nodes, there's a decent amount of throughput just attributed to the storage. So we want to make sure we're not interfering with that.
What about from the compounding standpoint? Did have at least one request noting that Hyper-V had some particular patterns of which commands were being combined in as compound requests in the scenario. And obviously, that's going to be dependent on the target and configuration. But I don't know if you have any comments along those lines.
Yeah, I'd have to look at the specifics, and
yeah,
I'm not sure.
Okay.
But if you've got questions around some of those things, I'm more than happy to try to find the right person or find the answer to it. Got them.
Anyone else?
So I don't know about the rest of the people. There's some confusion in my mind about which slides are just Hyper-V, which slides are just SMB3.
Mhm.
So for ODX and compound, did the Hyper-V team do anything at all
So in a lot of cases, I mean, we're really looking at this as a platform level functionality. So, for example, ODX. ODX is implemented by the client or the actual OS and implemented by the file server and all the way down through the stack. What Hyper-V did specifically is we made sure that we plumb that through the VHDX layer, all the way through the various stack. In a lot of cases, especially with SMB support, it's a combination of us working with the file server team and the SMB client team to enable these scenarios across the platform. Things like SMB live migration, obviously we did a lot of the work around that, but things like ODX and trim, largely those were done by the SMB client team, the SMB server team, and the OS team. We just inherit the benefit of it.
So I know I've seen research papers in terms of the change of workloads as the I/O goes through the guest OS to the hypervisor to the actual storage, but they've all been focused on NFS data stores. Have you guys published anything about how so a workload inside the OS is traditionally metadata intensive for a lot of things that we deal with or that I deal with, but when it hits the hypervisor, it becomes, you know, all block reads and writes. Have you guys published anything about what those workload characterizations look like from a Hyper-V perspective?
Nothing specific. So, I mean, it generally looks like a block request read write. We're not doing any particular optimization to say, oh, we're noticing that this is a SQL workload. Let's do some optimization around it. Within the VHDX stack, which is our latest stack, you can change some parameters, like you can say this VHDX is going to expose a 64K block range as opposed to a 8K, but we just look at it as a block access.
So do some of those parameters allow you to tweak things like write coalescing before it comes out of Hyper-V and goes to the SMB redirector, or that's just the way it is?
It's just the way it is.
Okay.
So we do implement and support the FUA bit, force unit access bit within a virtual machine, if it's on a SCSI controller. So if an application sends force unit access down through the SCSI controller, we will issue that all the way down as a FUA request all the way through the SMB stack. Other than that, it just looks like a standard block access, and we'll cache it in the virtual machine just as it normally would. Once it hits the hypervisor layer, it's going to be right through direct.
Thanks for all your questions, and thank you for coming today. Also, I wanted to make a big thank you, not just Taylor, but a number of folks from the Hyper-V test side as well came over. We had someone from the file services team bring our cluster in a box system so we could run Hyper-V and SQL Server as workloads and actually run them against some of your storage implementations. And I think it's been really instructive to us. We've always learned a lot. Things like I mentioned about the locking scenario. Last time we did that, we uncovered a big challenge for one of the implementers in that area. So at this event, I want to underscore this opportunity that we have to not only talk to someone like Taylor from the product team or other folks who've been involved, as you met the SMB file services team just a little while ago, but here at the event, you can do some testing, and I hope that's been helpful to you folks who've taken advantage of that. We have our synthetic test suites that we've been using. I continue to want to make a plug for that. If you don't have the latest copy, we'll give that to you. And the other thing I wanted to do is to mention that during the Plugfest, there's an opportunity to test. But for those of you who develop implementations and have more maturity, we'll invite you to IO Lab testing. Some limited group of folks last week have done some IO Lab testing or at other events where we could actually spend time testing, not just between presentations, but actually devoting some extended time. And for those of you who are able to stay through Friday, I don't know if any of you can, Friday's the doors are open just for testing this week. So interoperability testing only on Friday, no presentations. We want to give you that opportunity. So please do keep that in mind as you plan for future Plugfests. The other thing I wanted to do, since we have a few minutes and we're ramping down. Any last questions for Taylor before we? So I'll say thank you, Taylor. Thank you for all of your work.
Not a problem. And if you do have any other questions afterward, feel free to reach out, and these guys can put you in touch with myself or whoever else needs to be looped in.
Great. Thanks, Taylor.